this way, and my thumb is pointing up, which means there will be a force on this particle, a magnetic force pushing it upwards. As a result, this would kind of curve and actually make some sort of loop or some sort of curved circular path in that field. It doesn't add energy to it because this force and velocity are always 90 degrees, so it's not going to speed it up, not going to slow it down, just turn it. So it never gives it energy, it just changes its direction.
So when there's electric fields involved with that?
If there's electric fields, it matters which way they're pointing. So it's possible in part 2 of worksheet 3, you can say, well, there's an electric field pointing one way and a magnetic field pointing some other way, so the magnetic and electric force cancel out and the thing goes straight through. And that's what problem 4 has to do. Are you videoing this?
Yeah.
Is that helpful?
For notes later before the test, yeah.
Cool. Yeah.
You were saying that it doesn't speed up?
It does not speed up.
But, like, when you add the two vectors together...
But they're at 90 degrees.
Yeah.
They're always at 90 degrees.
So with that force, though.
Okay, so let's talk about this. Let's talk about it in terms of anything circular motion. If I have a velocity this way, and I have a force, or say a force upwards, my acceleration is upwards, yes? I have a velocity is to the right.
There's too much sexual tension on that. I can't.
What?
Do that on your video?
Probably. Facebook. No, I'm just kidding.
But they're at 90 degrees. I mean, if we go back to the beginning here and say, okay, if we have a velocity up and an acceleration down, it slows. We have a velocity up and an acceleration up, it speeds up. But we have a velocity up and an acceleration to the right, that just turns it.
Mm-hmm.
Remember that whole speeding up, slowing down, turn.
Circle,
turn.
circle.
Does that make sense? And so, since by definition this force and this velocity are always at right angles, because of the right-hand rule, there's no way that we're going to have an accelerated, we're not going to have a speeding up or slowing down part.
Is that when you talk about the perpendicular, is that the same thing?
Yeah. So if I were to draw that, if I were to try to draw this, I'd say velocity is this way, so that's the blue, and then I'd say, actually I'll make the black, and then the field is into the page, that would be the red, and then the force would be like that, or it'd actually probably be like that.
Okay.
90 degrees, yeah, so it is a cross product.
Okay.
Mathematically, if you guys learn cross product, it really is good. I mean, your force is QV cross. I mean, that's really what it is.
Yeah.
If I don't tell you that, you guys will freak out. Cross what?
Yeah.
So instead of that, I write it as magnetic force
So we could use like vectors.
QV sine theta, and this is the angle that's between these two. Most of the time, it's going to be 90 degrees. In this case, it would be 90 degrees, and this just simplifies it. Theta is 90, then this whole thing goes to 1.
What is that thing next to the F?
B.
So
whenever I talk about magnetic fields, magnetism, I use the letter B.
Okay.
Check.
So you have, like, an infinitely large magnetic field. Would the path that the charged particle takes always be a circle?
Well, it's going to be circular. If it's a really strong field, it'll spiral inwards and get closer. Kind of like if you would have a planet orbiting and there was a really big star pulling inwards, it would spiral inwards. If it was too weak, it might spiral outwards. If it was just the right strength for the mass and the original velocity, it could go in a circle.
So how hard is that to achieve to have it do a perfect circle?
I don't know. It has to be pretty precise if you want it to be maintained at that perfect circle. Because if it's slightly off, it might be spiraling inwards just slightly. Or spiraling out slightly. So it has to be pretty exact.
So, sorry. So it's like, you know how our planet follows like an elliptical trajectory?
Okay.
And do you think we'll ever get out of orbit?
No, we would have by now. Not if everything stays the way it is, no. If for some reason something changes and things do gradually change, so if the sun got less massive or more massive, or we could change some of that. So
Okay.
I don't foresee it gradually changing.
Okay, so on the diagram right there with that one. So we know that it's turning like that way.
The force is up and velocity that way.
Yeah. Can it be the opposite of that, such as?
So yeah, if the field was out of the page, I'd do the same thing. Velocity, the field's out of the page, and the force would be down. And that's totally possible. If the magnetic field was opposite, the force would be opposite.
And it would just reflect across.
Yeah.
Okay.
And if this was a negative, if we had a negative charge here, we do the exact same thing. velocity was this way, field on the page, force up, but since it's negative, a negative would actually feel force down. It feels an opposite force.
Okay.
Just like in electric fields, positive, negative feel opposite forces, in magnetic fields, positive, negative feel opposite.
Okay.
Back to the planet thing.
Yeah.
Are there any planets in our system that are slowly, like they're out of orbit or moving closer?
Not that I know. Just because we've been around a while enough, it probably would have already gone through its.
Do you think there might have been planets that had gone out of orbit?
Oh, definitely. I know Mars. Mars has a tendency of capturing moons and eventually just destroying them, pulling them. Like the 2 moons of Mars now are predicted to crash into Mars.
Will that increase its mass?
Yeah.
So it might like go out of its orbit.
Not drastically. I mean, the moons are pretty small. The captured asteroids are not really. Like you can jump off them. Like I think it's Phobos, which is one of them. Your ability to jump is the escape velocity. If you were on the surface of the moon, you could jump off it.
That's cool.
I know, kind of scary. Playing basketball and all of a sudden you're.
So will that collision between the moon and Mars like somehow knock it off its?
It's not. The moons aren't that big.
Okay.
Not to my knowledge. It may alter it. I don't know though.
So does the size of the magnetic field matter? Or like,
Yes.
do you ever have to calculate it? Or?
Yeah. Well, in this case, it's this value, and so either it's given, you're going to find the force, or you're given the force and you can find the field.
So the strength of the magnetic field is really dependent also on its size. How?
No, it's like it's basically it's a relation to how much force a charge feels in it. It would be dependent on what's making that field. So if we're talking about going back to this situation where we're actually the equation magnetic field is equal constant over 2 pi I over r. This is your equation for this. So your r is your distance away.
Yeah.
So the closer you are, the stronger the field. The more current in the wire, the stronger the field. So if you're talking about a field, you can create a stronger or weaker field. I have a big electromagnet here, and if I had more or less coils on here, I can make a stronger or weaker field. If I put more current through it, I can make a stronger or weaker field.
I know, like we learned at some point that you could find like a field area by using cross products or something in Berg.
I mean, if you go back to this equation,
Vectors.
yeah, I mean,
Would you
so
ever need to do that?
no. So officially, just your force is a vector, velocity is a vector, and field is a vector. And this charge is a scalar quantity. So really, you cross this to get another vector, and you add a scalar to it and multiply by a scalar. So if you have this vector and one of those vectors, you can find the other one. So if you do the velocity and the force on something, you can go and find the field. But really, the cross product of this multiplied by this, just some number, gives you the force vector. So in math, you're probably saying, oh, cross these 2 things. You can find the field by knowing the velocity and the force. But
Just for clarification, is that x a variable or just for cost product?
that's cross product. That's what I write it for you guys like this. I don't assume he knows anything about it. That's a cross. It's not an x. So you do not need to know that at all. But if you want to apply all that math, you've learned.
So, sorry, can you explain again with the magnetic field where you have the positive negative right there?
These 2, why they're
Yeah,
different?
why it's curving, because wouldn't there have to be an acceleration for it to curve?
There is. If there's a force, there's an acceleration upwards. So
Okay.
if it's here and there's a force this way, there's going to be an initial acceleration upwards. That'll cause it at some later point to maybe go like this, because it's not going to lose its horizontal velocity because there's no horizontal acceleration to speed up or slow it down. So it'll gain some sort of vertical velocity.
Okay, and if the 2 were switched with force and velocity, it would curve kind of like the opposite.
Yeah.
Okay.
But once the velocity is changed, then the force also changes. So as the velocity goes up, since these have to be at right angles, once the velocity changes, so does the force.
Okay,
So
that's why it curves
so it's
out.
like the velocity is this way, but the force is always at a right angle to it. So as one changes, the other one has to change.
Okay.
Even if the field is constant.
All right.
I know Q stands for charge, but does it stand for the mass or what?
The charge.
Charge.
No, that's a good question. So
That's always kind of confusing.
no, it's okay. So things you can quantify things a bunch of different ways. One way is to say there's a mass of something. So the mass of a proton 1.67 times 10 to the negative 27 kilograms. And really, what mass is how much is it attracted to other masses. It's a relative to the force of gravity. Mass has to do with force of gravity. It also has to do with inertia, like more mass, harder to move. But there's also something called charge, which is another fundamental quantity of things.
So it's like positive or negative.
Right, and how positive or negative. So that's the charge in coulombs.
Proton versus electron.
But they have the same charge. So the proton's plus this, and the electron's negative that. They have the same amount of charge. And that's fundamental. We can't, until you get to quantum physics, which you'll talk about next year, you can't get smaller than this.
Okay.
Do you chemistry?
Yes, it is.
The Milken oil drop experiment. Robert Milken, he had this microscope and he had this plate. This was positive and this was negative. He put a bunch of drops of oil in it, and he turned the voltage so that they would be suspended, so the force of gravity and the electric force pushing up would balance out on an oil droplet, and you look in his little microscope. I'm not sure what a microscope looks like that. And there's his eyeball here. Looking at those, and he would change this until they were balanced, and he's found that every single oil droplet had a charge that was a multiple of this. Either this times 1, this times 100, this times 203, but they all had that fundamental multiple charge. And so he said each thing had the smallest charge you could ever get would be that. There's no way you can get half that until you get to quantum physics, until you start breaking a proton apart. If it works. And you get either 1/3 or 2/3 of that. You have to break that into thirds.
When do we use those numbers, Berg?
These numbers?
Because I see them on my paper, but I don't know why I use them.
If you were going, so if you're talking about a proton going in a field, you would want to take this and put that in for Q. So normally we talk about charge being Q, just like we say this is M. So if we're talking about the force of gravity on the proton, we'd want to know, hey, what's the mass of the proton? We want to know
Only
the
if you're
charge.
talking about a proton.
Or for that, the mass of electrons is much smaller. As you know from chemistry, electrons are nothing.
Yeah.
Barely anything. The charges are the same though. So proton's just as positive as electron is negative.
Okay.
So if we're talking about electrons, we still use
So
this fundamental charge.
for a Q in the equation, otherwise, then we just put the mass in for like the object we're given.
If you're solving for mass, if you have an equation with mass in it, you'd say, what's the mass? What are you talking about? If you're talking about a proton, you'd use this mass.
Oh, but electron's different.
Electron's different mass. It's 9.11 electron mass. I think it's 9.11 times 10 to the negative 31 kilograms.
Oh wow.
Lacey, you're a chemistry person, right? I think that's the mass of an electron. It's much, much smaller. I mean, 1,000 times smaller.
But I'm talking about like a number 6 where they're not talking anything about protons or electrons.
What are they talking about?
It's like an alloy disc. So then do I just put the mass in for Q?
No. The Q is the charge. Don't use that equation. There is another equation used for this. So it is possible, instead of talking about a charge, if we had, let's say, another situation where we have a wire, and so there's a current flowing through here, and let's say the field in this case is out of the board. So out, I'd say fingers in direction of current, field out of the board. The force on this wire would be down. That'd be the magnetic force on a wire. You can think of this current as like a string of electrons or protons. And so the force on a wire. In this equation would be force on a wire, magnetic force on a wire is magnetic field, current, length, sine theta. So this is the length, how long it is. The current, this is in amps. This is in meters. And this is in Tesla.
Gotcha.
So that's the equation you're going to use, because you know the length, you know the current. I think there's so much current flowing through that alloy disc. That's the one you're going to use. Yeah.
When we have a magnetic field created by the wire, and so would there be like, so when you be dealing with two magnetic fields?
If you have two wires?
Or, no, because you have one being formed by the.
It depends on what you're talking about. In that problem, they're saying, what's the force on the wire? And it doesn't create a field that affects itself.
Right.
So you don't need to worry about it. You worry about the field it's in. If you're saying, oh, here's some other, maybe there's a positive charge here moving this way in this field next to this wire, then there would be two forces on that.
So we can just calculate them separately.
And then add them together as vectors. So maybe like one of them pushes out and the other one pushes down, and you say, okay, well, which way is it going to be pushed? But if we're talking about the force on something in it, we don't need to worry about the field it creates.
Did you ever ask us a question like that? Like there's two different magnetic fields.
Sort of. I mean, there's a question in worksheet 3, a front page, where there's like on the bottom there's two wires next to each other and what force they feel on each other. I would ask that type of question, where you'd have to figure out like.
Creates with the like charges moving around it, that doesn't affect the wire. It's only like the magnetic field around it, not these guys.
Right. It's kind of like you can't make a gravitational field that affects yourself. Charges can't move, like if you have an electric field, you can't just have a positive there that's going to push itself apart, an electron that's going to pull itself together. Like it doesn't. You can't create something that affects yourself.
And then so gravitational is proportional to R, but electric, I mean, magnetic is
Magnetic's
over
proportional to R,
and then
gravitational electrical proportional to R squared.
And then you were saying that you make a comment like it either goes like one way or the other in electric or something like that.
Oh, electric fields, positives go with the field, electrons go, or negatives go against the field.
Isn't that kind of the same?
Yeah, it's kind of true. It's just that it goes, positives go one way, electrons go the other, or negatives go the other way. But it's not with the field, it's 90 degrees to the field, which is a little confusing. I mean, electric fields are probably easier because there's no cross product, it's just a direct scalar quantity, or direct vector, vector, there's no cross to it.
And it's all tangent to the field line.
Yes, either parallel or anti-parallel. Yes. So really, all magnetism is electromagnet issue. So if I have a bar magnet, this can be oversimplified, but here's north, here's south, and so I have the field coming out, going this way from north to south. We can almost think of it as there's these protons, and really the spinning electrons are spinning around. Like all the electrons in a permanent magnet are spinning the same way. So there's all these loops. We kind of think that, well, we use the right-hand rule, they all spin the same way. If the field's going that way, that means the current might be kind of like going up and around. So like all the electrons are spinning the same way in the atoms, and so all these little loops of current going this way creates a magnetic field through that bar magnet. So we take that magnet and heat it up to cause it to vibrate more on the microscopic scale. And that vibration misaligns all of these, and so it breaks that magnetism.
So it makes it less.
Yeah, if you take a magnet and you heat it up, it becomes less magnetic. And if once it cools down, it doesn't realign. If you put it near another magnet, then it will force it to realign and you can then remagnetize.
That one I have no clue. It's actually just
Because the magnetic field will then force all those atoms back into an arrangement, and if something is magnetic, then it will hold that property. Most things, pretty much anything can be magnetized when it's in a very strong field. Have you ever seen the videos of the frogs?
Frogs.
Yeah, levitating frogs in magnetic fields. If they put a frog in a really strong magnetic field, it levitates. Because the atoms are aligned within that frog in such a way that they actually levitate.
Could you do that with us?
Can we watch the
You
YouTube
could.
video on it?
At the end.
Can we watch one of the snails do that too?
What?
I never knew the snails like could die when you did like the
Salt.
yeah.
You didn't know they did that.
Salt.
I have no idea what you're talking about.
You know when you put salt on snails and they like
Or unless you don't kill them, they come back really mad.
At a really slow pace. Like, it's
Frustrated
hard to outwalk
snails.
them.
Yes,
I never knew that before I moved here. We don't have
How come
snails.
some metals like don't stay magnetized? Like you can take a magnet and take out the block attached to the magnet.
so that it doesn't.
And then you take it out.
Certain properties of certain materials don't retain that alignment.
It's just the base of the material.
Based on that element, I don't know enough about to say why certain things do certain things.
I just spelled facility.
I spelled it wrong in the video.
You did? Okay.
Yeah, I spelled it wrong like 3 times. Yeah, 5 times.
I was getting really confused. Tell us
Like, the first time I felt like, oh, he just misspelled it, but when he did it like
I did. I know.
I
I feel off. I feel really stupid. That's how you spell it.
Okay.
You spelled the way you spelled it.
Yeah.
I spelled it. I spelled it wrong.
Don't trust anybody.
Yeah.
Alright.
No.
Were you saying that the core of the Earth is magnetized?
Yes.
And how is it magnetized if it's like super hot?
Isn't it core solid?
Oh, that's a
The
good.
core is solid, and it's partially, as far as I know, I'm not a geologist. From what I know, it's partially magnetized, not as strong as it could be, and also if you look at, and then we have this solid curve, but like between this, like there's a bunch of fluids, and there's certain convection currents that are spinning in a certain way with charged particles, and that kind of have a similar effect of electromagnetism. So I think it's both of those things. And it's really big. So even if it was less magnetized, it's still big, needs some magnetized, but I don't know for certain.
How deep do you have to go to get to like those fluids?
Like, what is it to the
It's like average.
mantle?
20 miles.
20 miles?
Yeah, it's
What's
deep.
And the deepest thing is someplace in Russia that's like 7 or 8 miles?
Is it just like magma?
I think so. I haven't been there in a long time. Maybe I'll go back there after I die. Yes.
So you can calculate the strength of an electric field by doing the force that test charge feels divided by the test charge.
Yeah, and that's at the field at that location.
Yeah, and then that's like the electric field constant times the two charges.
Yeah.
Divided by r squared. Why divided by q?
Because that's dividing by the test charge.
Oh, so that's the equation.
And so this would be the source charge. If you're talking about what's creating the field.
Okay.
So it really matters like a constant, what creates the field, and the distance away. Just like this is like the field, some constant, what creates the field, and the distance away.
And then the one that you have like equals f equals the one middle, the one in the middle one. Is that just the force e equation?
Yeah. And then this will cancel one of those.
And then got it. Yeah.
Ferromagnetism, is that just basically luck of the draw?
Ferromagnetism?
Yeah.
What do you mean luck of the draw?
Because like you can either be ferromagnetic if all your atoms combine.
Oh, ferromagnetism has to do with it's based on iron. Iron has the ability. So like if you are iron, you can be magnetized. So iron has magnetism. There's other types of ways to magnetize.
Yeah, but like you could be iron that's ferromagnetic and then anti-ferromagnetic. So like your atoms like alternate so that they balance itself out.
It means it would be still ferromagnetic because it can be magnetized.
It can be.
Yes.
If you like put an extra magnet.
So ferromagnetism is usually like something that has iron in it because iron has the ability to maintain its magnetic moment. Let's say the
I'm gonna
direction
put
it's
this on
going.
the page.
Even if it's not magnetized, it still could be magnetized.
Good review.
I wouldn't worry about ferromagnetism, but that just has to do with iron.
Is there anything else you need to know about magnetic fields?
Need to know?
Need to know.
You'll learn some stuff next week about if you have a changing magnetic field, you make current. I can show you guys that today. It's actually really weird stuff.
What are we doing?
Oh, yeah.
What are we doing next week?
There's crazy stuff. Yeah.
Oh, I just had a question. If you have two wires with current flowing in the same direction each wire, then is the point in the middle 0?
No, the point in the middle is not zero. It would be if they were going opposite direction.
If we're going opposite direction, the point in the middle is 0.
Or no, if they're in the same direction, the point in the middle is 0. Assuming equal distance and equal current.
In the very center, that would be 0.
Yes.
Everything else would be applied by the opposite wires.
And if you have two wires going in the same direction, they are attracted to each other. And if the wires current in different directions, they are repulsed by each other.
But it's 0 in the middle.
If you have two wires go with same amount of current going in the same direction, right hand rule would say, okay, this one may be coming at this way, and the other one they say it's going the opposite way. You can't use right and left, you have to use right and right. Which right and right. And so in the middle, it could cancel out.
Or if you used to like this, then this would be the right hand rule.
Sure, but that might be confusing.
Well, you just know it feels.
Yeah, but yeah, look, they cancel out. Yeah, there's a lot of different hand motions you can use. Anything else?
What is a paternity?
They have to be equal distance away from your dead in center.
But if they're not going the same way,
Then they would have a field that adds together in the middle.
got it.
It'd be like this. Like this.
Got it.
But they're repulsed from each other.
They are repulsed from each other. It's because one would have a field. You'd have to actually. I think one of the problems I had you guys do had to do with that.
Yeah, wait, when is that? Why is attracted and when are they repulsed again?
They're attracted when they're in the same direction. So if you look at number 4 on worksheet 3, we have current going up and current going down. Like those are repulsed by each other. So I have this wire here, and let's say I have another wire here.
Yeah.
Do you want to be repulsed or attracted?
Repulsed.
Okay, so that means the current would have to go downwards. Okay, so there's the field created, I'll call this 1 and this 2. So the field created by wire 1 at the location of wire 2 is out of the board. So when we use right hand rule, say current's flowing down, field out of the board, it would feel force this way. And if I say this has a right hand rule, so it would create a field that's coming out of the
Oh,
page
that's
here.
cool. Got it, yeah.
And so I'd go up, out of the page, this would feel force. And you can logic that pretty easily, saying if wire 1 is repulsed, then wire 2 is also, I mean, they're repulsed equal and opposite forces. They have to feel equal. Newton's third law says something applies a force, something applies an equal force backwards. So those are that way. If you had them both in the same direction, the opposite occur, they both attract to each other.
What is a potential difference?
It is a voltage difference. You're talking about number 4.
Yes. So what variable would you voltage?
Can we do number 4?
Yeah.
So Q.
When you say can we, you mean can I watch you on the board do it?
So would you plug it in for Q?
I would have to talk about that.
Okay.
You guys want to talk about 4?
Yes.
Makes me feel like that.
what should I erase? Everything? Are you guys okay?
Sure.